All right, so our last section of this polynomials unit, zeros of polynomial functions, is going to bring together everything that we have been doing so far. So our graphing in behavior, knowing what is happening at x-intercepts, that bounce, wiggle, cross, using our synthetic division, and factoring skills. So it's all of the things to bring them all together. So the first thing, which you might be wondering, why have we not talked about this before now if it's so fundamental? But it is going to be important for today. The fundamental theorem of algebra, and this is the fundamental theorem of algebra, tells us that a polynomial of nth degree has n roots. And this is for n being greater than 0. So what it's saying is whatever the degree of my polynomial is, that is how many x-intercepts it has to have. So if I have a line, so you've got something to the first degree, that polynomial has to cross that x-axis exactly once. It's a first degree polynomial, so it's going to have one root. If I have a second degree polynomial, it's going to have two roots. You got two x-axes. Same thing with third degree and so on. Now, something that you will see though is it doesn't always have to be two distinct roots. It could be the same root twice. Just like if I had left that as a parent function, it would have just bounced there at 0. If I have an x to the third, we know that just crosses once, and it's our parent function that looks like this, but there are 3 roots of 0. It has a multiplicity of 3. That's why it wiggles through there instead of just crossing like our line. So sometimes we don't have in roots that are distinct from each other. They could be the same root that's repeated. We could also end up with imaginary roots. So if I had used x squared plus 2 instead, it would have gone up 2, and it actually doesn't cross our real x-axis, and that's where imaginary numbers come from, is that with this fundamental theorem of algebra, it has to have in roots, so imaginary numbers made this be always true, where we could have x-intercepts that cross an imaginary axis. Kind of a weird concept. So that's going to help us, when we're finding all of our x-intercepts today, because we do want to know how many there are going to be. That helps us. So if we're given something like this, and we've got the directions, our factor completely. Hopefully our first thought is, okay, I could try factoring by grouping. So for the first 2, I could factor out an x squared, and then I'd have this 2x minus 11. But then we can already see I don't have any way of making this 18 and 11. There's not anything more that I can take out of this. So really what today is about is how do I handle something like this that is not factorable, but it's also not a quadratic, and so I can't just use the quadratic formula to find x-intercepts. I have to use something else. So we've been doing synthetic division. I could synthetically divide to see if something is an x-intercept, but I need a place to start because I don't really want to just start trying every number that exists. That's way too many, infinitely many numbers. So what's going to help us here, and for now I wouldn't write down this whole thing, it's kind of lengthy, but you'll have a few examples of coming up with those rational zeros. Our rational zero theorem tells us that if we're looking for possibilities, we can narrow it down using this. So our possible rational zeros of a polynomial can be found by putting all of the factors of the constant term, so usually that very last term, over all of the factors of the leading coefficient, which we know that leading term isn't always the first term, but the one that's the highest degree. So basically we're taking the lowest degree number and the highest degree and looking at those factors. Okay, so this is narrowing down our possibilities. These are the only rational zeros that could work. Okay, so back to the example that I had out earlier. So if I'm taking all of the factors of 18, so let's go ahead and write down all the factors of 18. We've got 1, 2, 3, 6, 9, and 18. So all the numbers that divide in. We won't always have so many. I'm looking at some bigger numbers here so that we can see what's happening. And then we've got all the factors of my leading coefficient. So just 1 and 2. And then the possible rational zero theorem is telling us that we're taking all of these factors of the constant. So possible zeros. It's always going to be plus or minus because technically -1 is a factor of 18 as well. We usually don't consider negatives, but we've got 1, 2, 3, 6, 9, and 18 all over the factors of 2. So what we are doing here is considering that we could have all of those things divided by 1. We could have all of those things divided by 2. So writing them all out individually, we would have a plus or minus, well, we're going to have all of these again, so 1, 2, 3, 6, 9, 18, but then we also have them all over 2, so you've got a 1/2, 2 over 2 is already there, it's 1, so I don't need to rewrite it. I've got 3 over 2, 6 over 2 is 3, it's already there, 9 over 2, and then 18 over 2 is 9, so it's already there. So here are all of my possible rational zeros. So I haven't actually found any x-intercepts, but I've narrowed down my possibilities from infinitely many to this group, which a lot of times it's a lot fewer than that, but I wanted us to see one that had several options. Okay, so now if I'm trying to factor this completely, now I am using synthetic division. It is trial and error, but I've got my errors are going to be narrowed down to these options. So I would always start low, which for our purposes, I'm never going to give you something where the x-intercepts are like 18 or 9. I'll keep them low to where you can find one within the first couple of tries. You're not trying forever. So we're just going to start with 1. We're using synthetic division, so setting up with your coefficients along the top. And if you still feel like your synthetic division is a little fuzzy, this should help because we'll do a lot of synthetic division here. So we're bringing down our 2, multiplying, bringing it down, multiplying, bringing it down, multiplying, bringing it down. Okay, so what we learned when we were doing synthetic division is that remainder of 0 tells us that x equals 1 is an x-intercept. So whatever's in the box, that's the x-intercept that we're testing, and it was a yes. So it's a beautiful day in the neighborhood, and that means that we're left with this 2x squared minus 9x minus 18. So the beautiful part of having a third degree polynomial is that I just needed to find one x-intercept, because once I found one, I don't have to use synthetic division anymore because I have a quadratic. So from here, I could use the quadratic formula, or I could factor. I'm going to go ahead and see if we can factor this. So we're looking for factors of -36 that add to be a -9. So let's see. We got 3 and 12. Yep, that works. Okay, so we've got a -12 and a +3. And then factoring by grouping. Oh, sorry. Okay, so we're good there. We got the same thing in parentheses both times. So we've got one of our factors is the 2x minus 3, plus 3, and the other factor is an x minus 6. Okay, so remember our directions were to factor completely. So the last factor, because we have 3 x-intercepts, it was to the third power, so our fundamental theorem of algebra tells us that there will be 3 roots. So our final thing, if we're putting this in factored form, is to consider that if x equals 1 is an x-intercept, that means that we also have the factor of x minus 1. So if I'm wanting to factor completely, I'm going to turn this sideways so I have enough room. We'll have our factor of x minus 1, and then we've got our 2x plus 3, and the x minus 6. So with a third degree polynomial, I am finding one x-intercept using synthetic division, and then after that I can factor my quadratic or use a quadratic formula, and then I've got all of my factors right there. Okay. So it happens sometimes. It's not always perfect to begin with, so I'm going to show you a full example that I worked earlier. So in this case, I could factor out a 2, but then it wasn't factorable by grouping, just like the first one. So I did need to look at my possible rational zeros. I've got all of my factors of 8, 1, 2, 4, and 8, all over the factors of 1. So it did help me to factor out that 2. It narrowed down what I was looking at. So this would just be a 1, 2, 4, and 8. But sometimes whatever you start with doesn't work. So for this one, I started with testing the x-intercept of 1, and I got a remainder of negative 18. So remember, this does tell us that f of 1 equals negative 18, but it doesn't tell us an x-intercept. I found one way that there is not an x-intercept. So what I would do from here is either draw a line through that last part so that we know, okay, it didn't work, or putting like an x through the whole thing, or putting an x through at least that x-intercept where we know that one did not work, and then we move on. We have to start with the same coefficients and test another value, and in this case, negative 1 did work, and so I, used synthetic division, got 0 as my remainder, and then that meant I was left with this quadratic. We could factor, and then I did have to remember that if x is negative 1 is an x-intercept, that means, oh, this should be positive. That should be an x plus 1. And then our x minus 4, x plus 2. Okay. So let's look at one where we are doing all of the things. Okay. So for this one, we're going to factor, solve for all of the roots, and we're going to graph it. Okay. So first we're going through our possible rational zeros. Of course, if you could factor it at the very beginning, that's always a good thing to try at the beginning, but this is not factorable by grouping. In fact, we're missing the x squared term, which is kind of different, but tells us that factoring by grouping would not help. So our possibilities, we've got the factors of 2 over the factors of 1. So we only have 4 options, and that happens sometimes where there are only 4 options. So we would start with 1. Why not? Oh, almost messed up there. Make sure if you've got something that's missing, we're missing an x squared, that we give it a 0 as a placeholder. Almost, but it didn't work. So we're drawing a line through it, crossing the whole thing out if we need to, and then going on to negative 1. Now, I have students every now and then that will just say, like, I've got a gut feeling, like I think, negative 2 is going to be an x-intercept, and if that's you, you're welcome to go with it. I'm just telling you that we're not going to have any that are super crazy. But you know what? Sometimes the first one that you find is a 2 or a negative 2, and so if you're just feeling lucky with that, go for it. It is trial and error either way. Okay, so negative 1 ended up working. So we were left with an x squared minus x minus 2. And then factoring this last bit, our two numbers that multiply to be negative 2 and add to be negative 1 would be a negative 2 and a positive 1. Okay, so if we're putting this all together, so this would be our answer to number 1. Our fully factored form, we've got this x minus 2, x plus 1, but then we also have our x-intercept up here of a negative 1, so that will also be an x plus 1. So we've got it in factored form, but if we're moving on to solving or graphing, it might be helpful to go ahead and combine those x plus 1s into an x plus 1 squared. So that would be the first part. We've got it fully factored. For part 2, I'm setting each of those factors equal to 0. So I've got my x minus 2 equals 0, my x plus 1 equals 0. So we get our x-intercepts of 2 and -1. Not sure why I circled all of that first part and then only, whatever. So then our last part, part 3, graphing what we've got. So we've got our 2 x-intercepts at 1 at 2 and 1 at -1. For the behavior at each one of those, 2 only had one factor, so it is going to cross. And then our -1 had a factor of 2, or multiplicity of 2, so it's going to bounce. I also know with my in behavior, so I could go back to the original and look here to see that it's positive and odd, so it's going to be like a line that is positive. So it's going to go from down to up. Or I could look at the factored form and add, but there's no need to mock multiply there when you've got the multiplied version right at the top. So it's going to go from down to up. So we'll start below the x-axis, bounce, and then cross. Now if we wanted to be a little bit more accurate, we did find a point along the way. We found when we plugged in 1, use synthetic division with 1, that we got the point 1, -4. So if we wanted to, we could plot a point here that at 1, it does go down to -4. But I do think it helps to at least confirm, we don't have to be that specific, it does confirm that our graph looks good.